All right. So we talked about proteins in the cell, but let's talk a little bit more about these phospholipids because they're so incredibly important that we get these, that we understand these. Okay, so we'll do another review about the components of phospholipids. We'll talk a little bit more, and I have a little video that shows you how these membranes are going to form spontaneously. Let's talk about this word spontaneously for a minute. When we're using this in this term in a scientific context, it means without added energy. Okay, so in everyday use, we might be like, oh yeah, Joe, he's so spontaneous. You never know what he's gonna do. He's unpredictable. He's just gonna up and decide to go hike Humphreys or whatever, right? But in the context of chemistry and biology, when we say spontaneous, we mean that these are the things that are going to happen without, they're kind of on their own. It doesn't have any context about how quickly it might happen, right? It might be spontaneous, but take a very long time to do. Okay, so we'll do that. And then we'll talk about what things determine how fluid a membrane might be and just how squishy our membranes can be. So this is a computer model based on the data, real data that's slowed down. We're going to watch this video. I think it's about a minute long. But in real time, this would take 20 nanoseconds. What we're seeing is this sorting out. We're getting the fatty acids are starting to become more centralized, where they're interacting with each other more. These little balls out here that kind of look like blueberries to me, those are representing our water molecules. So we can see that these phosphate groups, they're starting to sort out to interact with the water. And here we have the fatty acids. Okay, and this is really important that these do this because if we didn't have this spontaneous formation of the plasma membranes, life would look very different than it does. So let's kind of take a minute to think about this. And to kind of do some brainstorming about if your plasma membrane is too fluid, what would happen to a cell? And if the plasma membrane of a cell is too rigid, what might happen? Right. If you're too fluid, the membrane might fall apart. Meaning that the cell and could result in cell death. And we don't want that. If you're too rigid and there's not enough flexibility, then your membrane might break. Again, with the potential of resulting in cell death. So we need to find a Goldilocks zone. So when we are talking about plasma membranes, we need plasma membranes to be a little bit flexible so that we can have the adaptability. We can move those proteins around. We can allow various types of substances to enter the cells or to leave the cells. But we don't want to have too much flexibility where the cell would just plasma membrane would kind of fall apart. Okay, so let's think about some factors that could increase or decrease the flexibility of the plasma membrane. So here's a good example, a good hint for you. Here's some prickly pear cactus that is obviously in some snow. Here's some in a really sunny place. So temperature could definitely affect how fluid something is. So the hot means that there's more kinetic energy. So we're going to increase the fluidity. Those molecules are going to be moving around at a faster rate, so they're going to be bumping around more, so they're going to be more fluid. Composition. Of your plasma membrane. Okay. So specifically, what kinds of fatty acids do you have in those fatty acid tails of those phospholipids? Are they saturated? Or are they unsaturated? Gonna decrease your fluidity. So you're gonna become more rigid. Unsaturated, that's gonna increase your fluidity. Remember that saturated fats, they can pack together. Okay, so think about butter versus oil. These don't pack tight for the unsaturated, so that they're gonna, right, just like your olive oil being liquid at room temperature. They're gonna be more fluid.
Hello, it's me editing Julia, realizing that I made a mistake while I was in the classroom. So let's fix it now. Okay. Here we have a phospholipid. Here's our glycerol backbone. Here's our phosphate group. We remember that's the hydrophilic part. And here we have our fatty acid tails. That's the hydrophobic part. Hey, I'm scared. Okay, in this case, the fatty acids are very short. And when we have a short fatty acid, that's going to mean that the membrane overall is going to have higher fluidity. So we can kind of use this as an analogy. So the parts of my fingers that are overlapping don't have a lot of places to grip. There's not a lot of friction. It's going to be easy for those to slide apart. So let's go down here and draw out another phospholipid. Here, we'll start with our glycerol backbone. We'll add our phosphate group in there. And then we will have long fatty acid tails with lots of carbons. And that's going to mean that there's going to be lots of places for those fatty acid tails to overlap. It's going to take more energy for those molecular interactions to slide apart. And that's going to mean that overall our membrane is going to have lower fluidity, or if you like to say higher rigidity. Lower fluidity, higher rigidity is two ways to say the same thing.
Another factor is going to be the number, right? The amount of sterols, right? So how much cholesterol do you have in your membranes? And the effect of cholesterol depends on the temperature. So I won't say I won't have a little arrow. So when under hot temperatures, your cholesterol, if you have more cholesterol, that's going to decrease your fluidity. Under cold temperatures, it's going to increase your fluidity. The more cholesterol you have. All right. So again, thinking about different membranes. So our next chapter, we're going to talk a little bit about organelles. Well, actually, we're going to talk a lot about organelles and the jobs that all these organelles do. But right now, let's just focus in on the plasma membrane. This is the outside of the cell. And our endoplasmic reticulum is an organelle that we see inside of the cell, whose job it is to package and process various things, mostly proteins or lipids. Okay. So what we see, what is the Goldilocks fluidity for our endoplasmic reticulum, they have shorter fatty acid tails. I'm just going to do FA for fatty acid. These are most of their fatty acids are unsaturated. So having shorter, that's going to increase the fluidity. Having unsaturated fatty acids, that's going to increase the fluidity. So we can then think about, okay, so the job of a endoplasmic reticulum, it needs more flexibility, more fluidity compared to the plasma membrane. Okay. So for our plasma membrane, they're going to have longer fatty acids. They're going to be saturated. They're going to have a higher concentration of cholesterol, meaning that what we are going to see is less flexibility, right? More rigidity, and which is going to be stricter in allowing things to pass through that plasma membrane. Okay. And that makes sense. Okay. This is a tricky question. Okay, but I want you guys to think about it for a minute before I give you the answer. Could we have a phospholipid bilayer in a non-polar solvent? So could we make, let's just say, for example, this is going to be olive oil. Just because that's something that we're familiar with. If we take a whole bunch of phospholipid molecules, chuck it in some olive oil, will we see the same formation of this plasma membrane bilayer that we see when we put that in water, which is a polar solvent? Okay. So you might think, okay, we would have the fatty acid tails sticking out and interacting with our olive oil. Okay. And that's a good hypothesis. Okay. So if you thought about that, give yourself a cool kid point because that's a very good idea. But we also remember that our phosphate groups are all negatively charged. So if you've ever played with magnets, you know that when you try to put two magnets that the negative pole and the negative pole of a magnet together, they're going to repel each other. So what would actually happen is, yes, indeed, the fatty acid tails would flip around and we would have this kind of inside out thing. But because these are like charges, they're going to push against each other to get to move those like charges away from each other. So we would actually not see this setup. We would actually see these things being dispersed in our sea of olive oil. Okay. All right. Question though. Hey, Julia, excuse me, Julia. I'm confused now because you just said that these like charges are going to repel, but I just flipped back a few slides and I'm looking at what the plasma membrane looks like when we're in water, and it looks like this. So here we are. This is water. And we got water over here. So why aren't these negative charges then repelling each other? And now we have to go back and remember about the properties of water and remember that water is a polar molecule. So I'm gonna come over here. Okay, we got our oxygen, we got our two hydrogens. Oxygen has a partial negative charge, hydrogens have partial positive charges. This fancy letter D, this is the Greek letter delta. And in this case, it means partial charge. So it does kind of look like a little fancy letter D that's got like a little bit of frill to it. Okay, so I'll leave that there. Let's come back over here and look at what's going on here. So because water molecules, oopsies, let's do this. We have our partial positive charges. They're actually going to be interacting with the full negative charge of the phosphate groups. And so that this guy's negative charge and this guy's negative charge are kind of neutralized by the partial positive charges of the hydrogens in our water molecules. And so that effect of repelling isn't strong enough to actually push these phosphate groups apart. And that's why we need to have water be the solvent for life, is so that we can create these membranes. Because if we had a nonpolar substance, the phosphate groups would push themselves apart.